All right, and good morning, everybody, from Lowell Observatory. Welcome to Cosmic Coffee, a slightly delayed version of Cosmic Coffee this morning. It turns out we have a brand new firewall on our network, and it works really well on our network. And I was just cutting off the stream there. I had two copies of this running. We're a little bit rocky here this morning. So we're here this morning with Lowell astronomer Dr. Larry Wasserman and with Lowell historian Kevin Schindler. Since we come to you on Thursdays, next Thursday is Christmas Eve. Thursday after that is New Year's Eve. So this will be our final Cosmic Coffee of the year. And we'll be back with you the first Thursday after New Year's Day, which is going to be the 4th or something, plus or minus a day. So anyway, today we are going to cover one of the interesting current events going on right now. As you know, there's the so-called Great Conjunction of Jupiter and Saturn happening that reaches its closest approach on Monday, which also happens to be the winter solstice, at least here in the Northern Hemisphere. So today, we're going to talk with Kevin and Larry a little bit about the geometry of Earth's orbit at this time of year and what's going on in the sky, and some things you probably know about, as well as some slightly non-intuitive things associated with the motions of the Earth and the planets at this time of year. So we're going to start with Larry and talk about the seasons and the solstice and what's going on with Earth's orbit, and then we'll switch to Kevin for some discussion about the conjunction, both astronomically as well as the historical significance of these close planetary alignments. So thanks to you both for joining us. And Larry, let's start with just a general primer on Earth's orbit, solstices, equinoxes, and what's going on as we approach December 21st. And feel free to share a screen there if you like.
Okay, I will do that right now and bring up the slides.
Yep.
The current slide.
Looking good to me.
Okay, so Monday is the winter solstice. And then the question arises, what causes the seasons to begin with? Why do we have seasons? And there are related questions. Why is it the winter or the summer at solstice, but the spring and fall equinox? What are those? What's a solstice? What's an equinox? Well, it turns out that solstice and equinox are derived from Latin. And I never took Latin, but the equinox is derived from two Latin words, aequus, A-E-Q-U-U-S, and nox. Aequus means equal, and nox means night. So with the equinox, we have equal night and equal day. The solstice is derived from sol, which is the sun, and sistere, S-I-S-T-E-R-E, which is stand still. So with the equinox, the sun, at the solstice, the sun stands still when it reaches its highest point in the summer or its lowest in the winter. So that's where the names come from. Now, in the picture here, I hope you can see my mouse. You note that the Earth's axis is tilted with respect to the plane that's defined by the Earth's orbit. It doesn't stick up straight up 90 degrees from the plane, but it's tilted over by 23.5 degrees. And as the Earth goes around the sun during the year, the axis points to the same point in space during the entire year. And the third thing to note is that no matter where the Earth is in its orbit, the sun illuminates half the Earth. Okay, now what happens during the year? Let's start with the June solstice on the left here, where this is Earth's northern hemisphere summer. Note that the axis is tipped towards the sun, and as a result, first, the northern hemisphere sees a little more sun than the southern hemisphere. And second, if you think of the Earth rotating about its axis, which is shown in this figure, then as you come around through here, if you're on a fixed latitude line, you have less night because it's tipped towards you than you do here. So in the summer, we have longer days, shorter nights, and in the southern hemisphere, that's reversed. They have longer days and shorter nights. So the June solstice for the northern hemisphere is the summer, and in the southern hemisphere, it's winter. So if you were in Australia, you'd be heading into the first day of summer next week. Okay, what happens later in September? The axis is still pointed off to the right, but now the Earth is half illuminated. The illuminated part of the Earth goes through the axes, so that as you go around, you get an equal amount of sunlight and an equal amount of darkness. And that's the equinox, equal day and night. In December, the situation is basically reversed from what it is in June. You've got the axis now pointed away from the Earth. So what happened in the southern hemisphere here is now happening in the northern hemisphere here. You've got a long night and a short day. The sun is mostly over the southern hemisphere, and we get less sun. And we can see this from the next figure. This is a typical figure for the northern hemisphere, the sun in the winter and the sun in the summer. First, the days are longer, the sun has a longer arc, it spends more time above the horizon, and so you have more time for it to get warm than you do in the winter when you have a short arc. And also, when the sun is further over here, the sun hits the Earth at an angle and doesn't heat it as much. So in the winter, you get less heat from the sun and it's up less of the day. So it's colder than it is in the summer. I note that some people will tell you that the reason that the Earth is warmer in the summer is that the Earth is closer to the sun. And that is obviously not true, because when we have summer in the northern hemisphere, the southern hemisphere is having winter. And if we were closer to the sun, how could one hemisphere have summer and one have winter? So that may be commonly accepted by some people, but it's certainly not true. And I think that we'll let that be for the explanation of the seasons.
Right, and it actually turns out summer is when summer in the northern hemisphere is when Earth is close to aphelion, its farthest distance from the sun. So certainly it's doubly incorrect for the northern hemisphere.
It is.
And actually it's a dramatic effect, this 23-degree tilt. If you work out the trigonometry, I'm interested in solar radiation and solar variations. And if you look basically at the intensity of the sunlight hitting, say, Arizona in June, as opposed to December, it's a very substantial factor. The sunlight per unit area changes by not quite a factor of 2, from overhead sun in June to overhead sun or noontime sun in December. So it's a major effect, which is why the seasonal effects are so pronounced. So let's consider some of the maybe less obvious things. One of the interesting things is, although Monday is the shortest day of the year on the solstice, our earliest sunset here in Flagstaff was actually about 2 weeks ago.
Yep. I should mention before I leave this figure that the distance between the winter and the summer arc is twice the tilt. So this is a 47-degree difference in the sky, which is a very large difference between the summer and the winter. So that's an oddball thing. So then the question, as Jeff pointed out, is if the sunset, why is the earliest sunset in Flagstaff at the beginning of December and the latest sunrise is the beginning of January? One would think they'd be at the solstice, and they're not. And it's worse than that, because it varies with latitude. At 5 degrees north, the earliest sunset is in November, a month before the solstice. And at 55 degrees north, as you go north of Flagstaff, it's later, it's December 14th. So something very odd is going on here. And it's a very complicated problem, and I'm only going to sort of point at the right answer. The problem is that our clocks keep a 24-hour day. We keep what's called a mean solar day, which is an average day that has 24 hours, each hour of 3,600 seconds. And we believe that the sun does what our clocks do, but they don't. It turns out that, consider when the sun is at noon. The assumption is that that happens at when my clock says it's 12 o'clock noon, but that doesn't happen. Sometimes the sun at noon by my clock isn't quite at noon. It hasn't gotten there yet. And sometimes during the year, the sun has already passed noon. It's been there and gone. So if we define a real solar day as the time between the sun reaching its highest point in the sky, some solar days are more than 24 hours, and some solar days are less than 24 hours. And so what causes this? It's the combined effect of two different things. One is the fact that the Earth's orbit is not a circle, it's an ellipse, and the Earth moves at different speeds. It moves faster when it's closer to the sun and a little slower when it's further away. And in keeping with what we said before about the Earth being close to the sun not affecting the heating very much, the difference between the closest point and the furthest point for the Earth is not very much. The Earth's orbit is relatively circular. But there's enough that the speed of the Earth in its orbit varies a little bit. And that combined with the tilt of the axis leads to this business with the sun either leading or lagging your clock. And I really can't get into all the details here because very frankly, it's a real mess. And I don't want to try and explain it. But the effect of what's happening is the fact, due to the difference between where our clocks say the sun should be and where it really is. And that's what's causing this odd sunrise and sunset thing. But as I say, it's a very complicated problem, and I don't really want to spend an hour talking about it. But I will mention some things about it. The difference between the clock time and the time given by the actual sun is called the equation of time, and is shown in this slide. Note that where the watch is faster, that means that the watch got to noon before the sun did, or sunset for that matter. The watch says the sun should have set before it actually did. And it can lag or lead by up to 15 minutes or so. So it's a substantial difference. I note that this is also called the sundial equation because a sundial obviously gives the time where the sun is because it's based on the shadow of the sun. And if you want the correct clock time, if you have a sundial in your backyard, you have to go and apply this correction to it to get what should be your watch time. So the sundial can be off in November and in January, February by 15 minutes of where your watch says it is. Okay, another way of showing the equation of time is to make what's effectively a 3-parameter plot. On the x-axis, you plot the value from the equation of time, and on the y-axis, you plot the altitude of the sun on that date, and then you get a point for each day. And what you get is a very funny-looking plot called the analemma. And this is the analemma. And you'll note, if it's readable, if you get close, that the points on the left side are where the sun is faster than the sun is running fast relative to your clock. On the right is where it's running slow. The reason that the dates go round this way, they start at the bottom, go up over to the left, around, cross over to the right, go over the top, come down, then around to the right and down, successive days. Actually, they go the other way if you're going from January to December. So each point is where the sun is at a given time on that day. You can generate an analemma at any time. It's usually done at noon, but it doesn't have to be. So this figure appears on old maps very often, and I've never figured out why. You can actually do this for yourself. If you have a window where you can see the sun in the summer and the winter at a fixed time during the day. Say you have a window that allows you to see the sun when it's lowest in the winter, at highest in the summer, at some time during the day, and you could fix your head at some point and make a frame to hold your head and look out the window. And at each time on the same time every day or every fifth day or whenever you want, you look out at the sun, hopefully with some solar protection, and you make a dot on the window where the sun is. Over a year, you will draw an analemma. Nobody had done this ever for real, where you could see the sun, until an astronomer, an amateur astronomer who's interested in photography, named Dennis DeSico in 1978, decided he was going to try and photograph this. And what you do is you fix a camera and you spend a year, every seventh day, you take a picture of the sun and on the same piece of film. This is pre-CCD camera for a year. And he did this and he screwed it up and he had to do it again for another year. But he got the first photograph ever of an analemma. And there it is from his window in Boston at 8:30 in the morning. And he also took pictures that showed on the left where the summer sun rose and met the analemma, where the winter sun met it, and I guess this one's either spring or fall. So there's a picture, real honest to goodness. This actually happens. The sun is not where it's supposed to be at a given time, and that's the proof. Other people have taken pictures of analemma. It's become sort of a sport to take them over well-known places. So there's another one. But so the sun does funny things that we're not aware of as the Earth goes round, as our viewpoint changes. And I think that's it for that.
And, Larry, I was just going to mention something that, it's a reminder that our basic units of time that we use in daily life, the day, the month, the year, are all based on astronomy. And since time immemorial, we humans have tried to come up with a chronology that connects with those astronomical bodies. And given what's happened with the change of calendars over the years and everything, we're doing pretty well. I mean, the equation of time is still tricky, but overall, we've got systems that work pretty well for timekeeping as opposed to several hundred years ago.
Yeah, I mean, most people don't notice that the sun is 15 minutes wrong. Only astronomers are crazy enough to go out and do this sort of thing and say, oh, look, the sun isn't where it's advertised to be. Most people get along with that just fine and nobody cares and notices. But it's still interesting.
It is, and there's a couple of ways you can do the experiment. You reminded me of something, Larry, and I found the picture while you were talking about the dots on the window, and that's a neat way of doing the analemma. You can also kind of do it with a sundial, and I did that 13 years ago now with my kids out here in front of my residence at Lowell, and I'll just share this fairly cute picture fairly quickly. So this was halfway in, and there you can see the gnomon we were using, and we started in winter and basically every 2 weeks hammered a stake in. So blue is the winter, green is spring, and we'd just gotten to summer. This was right after the solstice, and you can see that figure eight starting to form. And over the rest of the year, it traced out this figure eight on the ground. So if you're watching and have kiddos and want a neat project they can do over the course of an entire year, you can do that. The only problem with our experiment is the gnomon, I think it got impacted by a soccer ball at some point in September. So our analemma had an unconformity in it.
So a listing analemma.
So just a couple of things on the chat feed. There's one more of a comment for Larry that's come in from someone named Mark Wasserman, and the comment is, "Hi, Dad." So there we are. And then a question of whether the seasonal variations we observe have anything to do with the polar vortex. I can probably answer that one. No, that's a weather effect due more to the fluctuation of the jet stream, and there's been some interesting discussion about the relationship between the evolution of the jet stream as the climate warms and the increasing frequency of polar vortices leading to these extreme cold snaps that we've seen in recent years. So now let's talk about the conjunction itself. We'll switch over to Kevin for what's going on in the sky that's just happening to be at the solstice, but it's also a sort of an effect and an impact of Earth's orbit and the particular geometry of Earth and planets.
Right. So let me share a program here. And are you seeing that okay?
Yep.
Okay. So if you've been going outside over the last few weeks, you've noticed two dots that are getting closer. And those dots, the brighter one is Jupiter and the fainter one is Saturn. And this picture is from last night, and this isn't the greatest pictures, but this is just with a cell phone, my cell phone, iPhone, holding it up next to our Dyer telescope dome. And we've noticed these two dots. If you go out, they're getting closer and closer. And I encourage everybody to go out every night and look at this, because we're going to see them continue to get closer up to Monday. And you want to go outside right after sunset and look low in the sky to the southwest, and you'll see these. The moon also just happens to be at that area of the sky. Tonight, the moon is going to be above the two rather than below. But these two planets getting close together is something called a conjunction. And a conjunction is just, from our vantage point on Earth, when two or more objects in space appear to be getting close to each other. And I say appear to be because, we're looking out and seeing things two-dimensionally. So, if I have a little video to demonstrate this, Jupiter is something like 440 million miles away, and Saturn is twice that distance. So while we're seeing it two-dimensionally, they look like they're gonna, touch each other. They're still very far away. And to show this, I've got this video that Danielle Adams, our Deputy Director for Marketing and Communications, put together. And let me just play this. We have the orbits of the planets, and we can see how the Earth is going around Jupiter and Saturn. And when they line up just right here, you can see that from our perspective, they're going to look like they're close to each other. Again, if you could see them from the side, you would see that they were far away. So it's just the way we look at these things, but it's really pretty fascinating to see this, and we understand why the ancients named these bodies planets, which is Greek for the wanderers, because when they viewed things just like we can do over the next few nights and beyond, we can see Jupiter and Saturn wandering against the background stars. And so this is a phenomenon the sky watchers have been looking at for a long time. So a conjunction is just two or more bodies, as we see from Earth, getting close together. This is a conjunction that happened more than half a century ago. And one of our longtime astronomers, E.C. Slifer, captured this. It's the moon on the left and the much more distant planet Mars on the right. And I think this was an occultation when the moon actually passed in front of Mars. But from our viewpoint on this night, these two objects were very close together. Now, there's another term that we've been hearing a lot this year, and that's a great conjunction. And a great conjunction has been thrown out there to mean a conjunction of two things when it's specifically Jupiter and Saturn, the two largest planets in our solar system. And these great conjunctions happen about every 20 years. But because, as Larry was talking about before, nothing is perfect out there. Our orbits are all different. They're not perfect circles. They're elliptical. Our planets, while they're all in the same basic plane, they're not exactly in that plane. They're a little above or below. And so the geometry, everything isn't exactly the same. So sometime you have these events where Jupiter and Saturn get closer together. Sometimes they're not as close together. But what we're going to see over the ensuing nights, we can see from September how far apart they were. And then as the months went on, they're getting closer and closer till the 21st. They'll look almost like they're on top of each other. Our eyes, and this is something we can talk about a little bit later, the resolving power of our eyes and whether we'll be able to, if those two bodies will look as one or if we can resolve them. But they're going to get really close on the 21st. And Larry is an expert at looking at the position of things in space. And last week he shared this with staff about how close Jupiter and Saturn will appear. If we remember that, if we look at the full moon is 30 arc minutes, a unit of measure called arc minute, and keep in mind is 30. And so from December 28th to the 26th, this number shows how close Jupiter and Saturn will appear in the sky to each other. And so from the 18th to 26th, Jupiter and Saturn will be closer together than the diameter of the moon. And so that starts just tomorrow till we get to the 21st and 22nd. And this is universal time. So in Flagstaff, we subtract 7 hours for that. So for local time, the 6.3 is actually on the 21st. But that's about 1/5 the diameter of the full moon. That's how close they're going to be together, which is going to be pretty neat to see. We haven't seen them this close since Galileo himself in 1623, who had first pointed a telescope at the heavens in 1609. So this was in the early days of the telescopes. Not since then have we had one of these great conjunctions of Jupiter and Saturn that they were this close in the sky. Now, in that year, they were really close to the sun, and they weren't really in the night sky. You couldn't see them. So you have to go back to 1226 when another not so sky watcher, Genghis Khan, was at the end of his rule. Not since then have we seen a great conjunction where Jupiter and Saturn were this close in the night sky. So it's a really unusual event. And, when you go outside, you look and see these two dots, and that's all you're seeing. But when you realize what you're looking at and seeing just like what the ancients did and seeing what Galileo and others did is a pretty neat thing to see. So what's the sky going to look like? And this is the 21st, and this is a naked eye view. Take away the labels that won't be there, and you'll see Jupiter and Saturn. Again, this is going to be really low on the southwestern horizon, and we're only going to have an hour or two after dark that you're going to be able to see them, depending on, if there are trees in the way and buildings and such. So it's best to find a place that is devoid of that kind of thing. So you'll see those two up in the sky really low. What I think is really neat about this is if you're an amateur astronomer or if you have your own telescope at home, you'll be able to look at Jupiter and Saturn through a small telescope and see them both in the same field of view, which is a very unusual thing. And so you'll be able to see Jupiter with several of its moons, the Galilean moons, the 4 largest moons will be lined up. One of them, Ganymede, you won't really be able to see because it'll be in front of Jupiter. And then Saturn with a couple of its moons, you'll see in the same field view. So, it's a neat phenomenon. I think one of the things that makes astronomy so much fun and is the oldest science is that while it's great to have telescopes and binoculars and such, you don't need that to just go outside and look up and notice these things happening. And so this is a great opportunity to do that.
It certainly is. And so interesting question you've raised about whether on the 21st we'll be able to see the two planets distinctly. That's been raised a lot in the media. We were talking about that before. And I think and that sort of connects to the final topic for today's show, which is the historical significance of these planetary alignments and so-called Christmas stars and all of that. I think it's pretty clear even on the 21st, we will clearly be able to see two objects because the resolving power of your eye is about an arc minute, and they're going to be 6 arc minutes apart. So you should definitely still see two separate objects, not one single bright object. But we've seen some examples of conjunctions in the past that figure prominently in history, and so Kevin can tell us a little bit about that too, I think.
Right. Well, this great conjunction, we haven't had. We have them every 20 years, but haven't had a really good one in hundreds of years, and one in the night sky for even longer. So that's really interesting, but it really ties in an interesting cultural aspect also, because this is happening just a few days before Christmas. And, when we get around Christmas time, one of the most iconic images of the Christmas season is the Christmas star, the Star of Bethlehem. You see it on holiday cards, on cartoon, animations of the season, movies. We see it all over the place, and it goes back to the Bible, where it mentions a couple times in Matthew about the wise men being guided by this star, and there's not a lot of detail, and so. Astronomers for years have thought, what might this have been? Was it just symbolic? Or if it was a real astronomical body, what might it have been? And this really makes the conjunction this year really fascinating, and why the media in so many places have called it the Christmas star, because of this connection, and I'll tell you why in a minute. So for centuries, astronomers have tried to figure this out. What might this have been? If it was actually, was it actually a star as we know it today? And, terms change over time. So the word star, as we use it today, certainly has evolved. Centuries ago, a star, could be anything in the sky. And so was it an actual star as we think about it today? Probably not. Because if it was, the ancient sky observers would have recorded it. Plus, we understand enough about stars that there's no, general star that we know of that is that bright, as described. So, what might it have been? Well, some suggestions have said maybe it was a comet that was in the night sky. This is a picture of Comet Neowise that Jim Cole of the Observatory took just a couple months back. And this is above our Giovanni Open Deck Observatory. So scholars have looked back in time, and, it's tricky because we don't even know when Jesus was actually born. It's a range of time because the records were incomplete. So anywhere from 7 BC, to several years newer. And so scholars have looked back at observations made by ancient observers, because they were looking at the sky was really important to them, and the location of planets and other things in the sky was very important. And the records just don't indicate there was any really good comet during the right period of time. And even if there was, ancients saw comets as doom, not, this coming of something great. And so it's unlikely if they had seen a comet, they would have followed that. They would have gone in the other direction probably, even if there was one. So what's another possibility? I mentioned star, some sort of star. So maybe not a typical star as we have in the night sky, but maybe a star that had exploded, like a supernova. We have a large star exploding. And these have been experienced over time periodically. This is Tycho Brahe looking at one, And you can see how it's depicted here in the upper left, a little bit brighter than everything around it. And again, scholars have looked back, and if the sky observers at the time had seen something like this, they would have recorded it, because this would have been a big deal. But they recorded nothing like this. Now we have, today we're able to see remnants of these events that have happened. This is one. This is called the Crab Nebula, and this was taken with the Lowell Discovery Telescope a few years back. This isn't what it looks like with the naked eye. You need a telescope. We do see remnants of these events, but we don't have any evidence by the ancient sky observers that anything like that took place during the period of time when they think Jesus was born. So what's another possibility? Well, another one isn't quite as obvious initially, because, for a lot of us, when we think about the Christmas star, we expect they would have seen this big bright thing in the sky, that was a beacon. But again, remember, to the people back then, the ancients, they looked at the planets, and they looked at the position of planets and how it changed over time, and that had a lot of significance to them. And so it's very possible that something maybe not as visually dramatic, but something that had a lot of meaning behind it, could have been this so-called Star of Bethlehem. And so maybe the Magi were looking up, just like our Deputy Director for Education, Samantha Gorney, did last night. There's a picture last night looking up at the moon and Jupiter and Saturn. Maybe they did the same thing and saw this conjunction of planets, just like we're having this year in 2020. And it turns out, if we go back in time, there were a few conjunctions that took place during that span of time when Jesus was born. And one was in 7 BC or BCE, before the Christian era. And Jupiter and Saturn, just like this year, Jupiter and Saturn were close together. And they also were in the constellation Pisces, which was very important. That was a symbol of Judea. And so that had added significance. So it wasn't necessarily this big bright thing as we think of, but maybe it was because these two things were close together, had a lot of meaning. Perhaps that's why that's the origin of the Star of Bethlehem. We don't know. We don't know, but it whenever we can connect science and culture and religion and have a conversation and try to look at what these things are, I think it's a fascinating conversation, and it gets us all thinking about the universe around us in a lot of different ways. And I was just going to mention, before we kind of go to an open discussion, that on Monday, when Jupiter and Saturn get closest, we're going to be doing a live stream event starting at 5 p.m. Mountain Standard Time. And we're going to have Larry and several other astronomers and educators explaining the conjunction, talking about historic aspects of it. But we're also going to be doing live views in and out the whole time until we can't see it anymore, until those two set. We're going to be looking at them through telescopes. It's going to be a really fun event. So we encourage everybody to join. So let me stop sharing here, then we can turn it over to some open discussion here.
Right, we'll take any questions at this point, and it certainly is cool to have the opportunity to see both of these planets in the same telescope view. And as you say, Kevin, a very neat that we have the understanding and the tools to propagate the motions of the celestial objects backward and forward to see what was really going on in the sky in 7 BC. So at this point, I'll just remind everybody that is 5 o'clock p.m. this coming Monday, Mountain Standard Time. So 4 o'clock for our friends in Seattle. I was just speaking to on a different topic last night. And they're 7 o'clock if you're over in the Eastern time zone. And we will be broadcasting for those 2 hours with some live views from the Giovanni Open Deck Observatory and with lots of commentary from our educators and astronomers. So be sure to join us for that. I'll ask for any final questions today from our viewers before we sign off? And just a reminder again, as I said at the start of the show, the next 2 Thursdays are Christmas Eve and New Year's Eve. And so Cosmic Coffee will take a holiday hiatus and will be, say, after the new year. Question came in from DP. And I think, did you say it was Jupiter and Saturn in 7 BC? It was those two, right?
Right. Yeah. So just like we have
backwards relative